So this is the sliding block assessment. In this situation, we have a block that's sliding through this kind of course. Its initial velocity is 6 meters per second. It's going to go down 10 meters, go back up 4 meters, and then go over a rough surface with a coefficient of friction of 0.7 that's 8 meters long. So the first thing we need to figure out here is what the speed of the block is going to be at point B. In order to do that, we're going to use our energy concept. And since we know that energy is always conserved, we know that energy at A has to be equal to the energy at B. And we know that energy at A has two components, a kinetic component because it's moving, and a gravitational potential component because it is elevated. So we're going to write K plus UG. And our energy at B, because its height is 0, doesn't have any gravitational potential. It only has a kinetic component. So we're just going to write K. And the formulas for these are K is 1/2 mv squared plus UG is mgh, which is going to equal our 1/2 mv squared again. So we know, since we have an m in each of these pieces, we can get rid of that. Just makes it simpler to figure this out. Our initial velocity here at A is 6 meters per second. So that's going to end up giving us a v squared, so 6 squared of 36, plus gh is just going to be 10 times, because g is always 10, and h is also 10. So 10 times 10 is 100, equals 1/2 v squared. And we don't know what this v is, and that's our one variable we're solving for. So that's going to stay as a v, and we're not going to input anything for that. So when we plug this all together and work that out, we get 118 will equal 1/2 v squared, and multiply by 2, you get 232 equals v squared, and you get v equals 15.23 meters per second. So that's the speed of the block at B. You can write V sub B is 15.23 meters per second. So the next part of this that we need to solve is if the block reaches point D, because we don't know if this friction is going to be enough to stop the block from moving anymore. So we can use our energy concept again, where energy at A is equal to energy at D. And we know energy at A is just a kinetic component and a gravitational potential component, as we talked about earlier. And energy at D is going to be a gravitational potential because it is elevated at D, a work done by friction component because it's going over that frictionless in between A and D, and also a kinetic component. But we don't know if this guy even exists. So what we can do is work out the equation without our kinetic, and if this side, if our energy at A ends up being bigger than our energy at D, we know that the reason that there's less energy on the D side is because we never included the kinetic component. So there must be a kinetic component at D. But if the energy at D is equal to the energy at A when we don't calculate the kinetic component, we know that there is no kinetic component. And if the energy at D is greater than the energy at A, we know that the kinetic component, that actually it stopped somewhere in the middle and not at D. So we're going to leave the kinetic component out, and the way this problem works out is going to lead us to find if that kinetic component even exists. So we'll go again, 1/2 mv squared equals mgh, oh no, my bad, plus mgh equals mgh plus, and work done by friction is force times distance, or the frictional force times the distance it's applied over. And we don't have our frictional force, but what we do know is that because friction equals our coefficient of friction times the normal force, and because the normal force equals mg, we can substitute in mg for the normal force, and then we can substitute in mu mg for friction. So we know that friction d is actually going to be mu mg d. So we'll write that out again. Mu mg d. So we have m in each part of this, so we can get rid of our m's. Makes it simpler to work out. The next part we're going to do is start plugging in our variables. So we know that we calculated our energy at A before, and that number was 118. So this guy is going to be 118 because nothing has changed from what we did in the last step. But we have a new GH, a new GH, which is 10 times 4 meters. So I'll just write 40. 10 times 4, 40. Plus mu, which we talked about earlier was 0.7, times g, which is 10, and times d, which is 8. So we'll get 118 equals 40 plus 56. 118 equals 96. Now, because our 118 is actually greater than the 96, we know that there's got to be something else, because these numbers have to be equal. They have to. So what we're forgetting is our kinetic component, which we never include in the first place. So because our energy at A is greater than our energy at D when we leave out the kinetic component, that means that the kinetic component must exist at D, which means that, yes, the block is moving at D. So figure that out. That's great. Next thing we want to do is actually find out how fast is the block moving at D. So for this, we're going to use our same setup as we did before, but we can just leave it at this end step, and then, let me just, 118 equals 96. Plus k. So we know that our k exists now. So 118 equals 96 plus 1/2 mv squared. Well, what I'm doing is kind of flawed because I have to include the k back here. So then we'll get plus 1/2 mv squared here, plus 1/2 mv squared here, and then the m's are going to go away like we did before, And so then we've got our plus 1/2 v squared hanging out. So now we're going to do 118 minus 96 in order to get the v squared on its own side, which gives us a 44. Nope, gives us a 22. 1/2 v squared. Multiply by 2 to get rid of the half. It's going to get 44 equals v squared. And then square root both sides. And we find that 6.63 equals v. That's 6.63 meters per second. So this is the speed of the block at d.